Okay, let's now proceed to resultants of force systems. Now, if you try to remember that we already have taken the resultant of a force system of concurrent forces. So when we're speaking again of concurrent force systems, the line of action of all these forces intersect at a common point. Now, so at this time, let us try to consider now the principles of moment. So how are we going to determine the moment of a force about any point? Now, so the moment of a force is the tendency of a force to rotate the body on which it acts about a given point or axis. So let's try to consider now that this is now your point O, or that is now the axis of your point O. Now, how are we going to determine the moment of this force about point O? So, when we're speaking of a moment, so this is now the perpendicular distance from that point or axis to the line of action of the force. So if this is now the line of action of the force, the perpendicular distance about that point, and let us try to consider now that the perpendicular distance about that point or about that axis is D. So this is now 90 degrees, and this is equal to D. Hence, the moment of the force F about point O is now equal to the perpendicular distance from that point to the line of axis of the force F. And this is therefore equal to the force multiply this one by the perpendicular distance. So what is now this D? So your D in here is known as the moment arm. So this is known as the moment arm of the force, or the lever arm. So it's the lever arm of that particular force about that point. Now, since moment has direction, so we now have the moment in here. So since moment have direction, then your moment in here is a vector quantity. So this is known as a vector quantity. So there are cases that the perpendicular forces, the perpendicular distance of a force is hard to determine. So we have to apply your Varignon's theorem. So in your Varignon's theorem, the moment of a force, so this is now the moment of a force is equal. So this is now equal to the moment sum of its components about that point. Now, so let us try to consider a force F. So we have now your force F. So we have this is now the x-axis and the y-axis. So let us try to determine the moment of a force about that point. So considering now that this is now the force. This is therefore the force F. So the moment of this force F about point O is now equal to the magnitude of this force multiply this one by the perpendicular distance from the moment center to the line of action of the force. So this is now the line of action of the force, and this is therefore the perpendicular distance from the line of action to point O. So your point O in here is therefore known as the moment center. So that is now your point O is the moment center. So when we say moment center, so that is the point where the force is to be rotated. Moment center. So your force in here, the moment of the force about point O is now equal to F multiply this one by T. So according to Varignon's theorem, the moment of a force is now equal to the moment sum of its components about that point. So if you try to take a look in here now, so let us try to determine now the components of this force. So we have the y axis, and let us try to consider this one is now your x-axis. That is the x-axis, and this is now the y-axis. So let us try to resolve the component of this force along the x-axis and along the y-axis. So the component of the force can be resolved at any point along its line of action, but you try to take note that when you are resolving the component of a force, you should have to know the coordinates of that point where the force F is resolved. So I'm just going to resolve the component of this force about this point. So that at this point in here, we now have the component along the y-axis. So this is now your F sub y. Okay, so or I'm just going to resolve it at any point along the line of action, provided that the coordinates of that point is known. So at this point, I'm going to resolve that component of the force about this point. So we have now your component in the y-axis. So that is now your Fy. And the component in the x-axis, so let's try to consider this one in here as your f of x. Now such that the distance of the component in the y-axis is equal to x. So let's try to consider now that the distance or the perpendicular distance, this is now equal to x. And the distance of f of x from the x-axis is now equal to y. So applying now your Varignon's theorem, the moment of that force about point O is now equal to the moment sum of its components about that point. So this is now your point O. So we now have about point O, your fx in here is now having a moment about point O and the perpendicular distance from the line of action of that force to the moment center is now equal to y. So this is the line of, you can extend the line of action of the force, and that one in there is now equal to y. So we now have fx multiply this one by y. And then we now have plus, okay, so we have your fy multiply this one by fy multiply this one by x. So that is now your Varignon's theorem. The moment of a force is equal to the moment sum of its components. Okay, so since moment has direction, we are told before that it is a vector quantity. So if this is now your force F, and if you're going to get moment about point A, so this is equal to the force F multiply this one by force F multiply this one by the moment arm, or we call that one as the lever arm. So that is equal to force multiply this one by the moment arm. So what is therefore the direction of this force about point A? So you try to take note that this force in here is now, so this is now the line of action. So this is going counterclockwise about point A. So that is counterclockwise about point A. So the moment of this force about point B. So that is about point B. So we now have the moment arm of this force about point B. So let's try to consider that this one in here is B sub 1. So the moment of the force F about point B is now equal to the magnitude of this force, which is equal to F, multiply this one by the moment arm, which is now your D1. So you try to take note in here now that this, the direction of this force about point D is now going clockwise. So the direction of that moment is now a clockwise moment. Now, if you're getting moment of a force, you can assume clockwise moment as positive or counterclockwise moment as positive. Unless otherwise, it is specified on the problem that use clockwise moment as positive or use counterclockwise moment as positive. So if you assume clockwise moment as positive, then automatically counterclockwise moments are negative. And if you assume counterclockwise moment is positive, then clockwise moments in there are negative. Okay, determine the moment of the force F, which is your force F, which is equal to 40I plus 80J about point O. So this is now your point O. Okay, so how are we going to determine now the moment of this force about point O? So let us now apply your Varignon's theorem. Because if you try to take a look at this point, now the perpendicular distance, okay, from the moment center, supposed to be, this is the line of action of the force F. And this is the perpendicular distance or the moment arm of the force, which is equal to D. So it is hard to determine the moment arm or the lever arm of this force. So it is difficult to determine, the moment arm or the lever arm of this force about point O. So let us try to apply now your Varignon's theorem. So we have to determine the components of the force. So the components of F, which is equal to of the force F, is equal to, so we have now your F of X is now equal to 40 newtons, and your F of Y is now equal to 80 newtons. So you try to go back on how we express forces in its Cartesian vector form. So this is Fxi plus Fyj. So the component in the x-axis is now your 40, and the component in the y-axis is now your 80 newtons. Applying now your Varignon's theorem. So let's try to apply now your Varignon's theorem. So this point, since we know the coordinate at this point, so the component of that force can be resolved at the point where the x and y coordinates are known. We have your Fx. So this is now your f of x. And your f of x in here is now equal to 40 newtons. And then we now have your f of y. So your f of y is equal to 80 newtons. So that is 80 newtons. We have the x, and this is now your y. And we now have this is equal to 360 millimeter. That is 360 millimeter, or this is 0.36 meter. And this one is 150 millimeter, or that is 0.15 meter. So we are now ready to determine the moment of the force F about point O. Now, assuming counterclockwise moment as positive, moment, so that is counterclockwise moment as positive, then the moment of this force about point O is now equal to, so we have now your Fx is going clockwise about point O. So we'll only have to limit it to the line of action of the force. And therefore, we have negative Fx, multiply this one by, so the moment arm is 0.15. So this is 0.15 meters. And your Fy is going counterclockwise about point 0. So that is positive Fy multiply this one by the moment arm is 0.36 meters. Hence, the moment of this force is now equal to negative 40 multiply this one by 0.15 plus 80 multiply this one by 0.36. And the moment of this force about 0.0 is now equal to 22.8 Newton meter. So that is now, so the unit of a moment is force and a distance. So it is the unit of a force and the unit of at the distance. So that is Newton meter. Since we get a positive value, hence the moment of this force about 0.0 is counterclockwise because we assume counterclockwise moment to be positive. So that is now counterclockwise. Ni at nagparang mit man day ta. Kaso pangikat ko na kwa itas ko lagta. Dito ni.
Ay, open namin dito. Cancel.
About that point. Okay, so we have another solution using the normal and tangential components. When we say normal and tangential components, the component of this force perpendicular to F, so that is the normal components. And the component of this force along the line of action of the force F, so that is the tangential components. Okay, so let us try to draw now or extend the line of action of this force F. So this is now the line of action of the force F. And perpendicular to the line of action of this force F is known as your normal component. And this is therefore your Fn. And the component along the line of action of the force F is your tangential components. So this is the tangential component of the force F, which is equal to. So let us try to get now the tangential components of the force F. So we have, so this is therefore the line of action of the force F. So we have the line of action of the force F. So we now have the line of action of the force F. So we now have the tangential component. So this is now the tangential component is in the direction of the force F. So let's consider this one in here is now the tangential component, or that is equal to Ft. Now, so we now have the tangent. Okay, so we now have your Ft. Okay, so we have your Ft in this direction. Okay, and that is now your f of n. This is now your f of n. So we have this, okay, so that is the normal component, and this is now the tangential components. So we have the force F. Now take note in here that this slope in here is now equal to 150 over 30, so that is equal to 5, and 360 over 30, so that one is now equal to 12. So from this point in here, let us try to consider that this angle in here is equal to theta. Okay, so this is now your F. This is now your Ft. So that is now equal to theta. Now, such that this, let us try to consider that this angle in here is alpha. So that if you try to get now your alpha, this is equal to the arc tangent of 5 all over 12. That is now the arc tangent of 5 all over 12. So that is equal to 22.6 degrees. Now, I was going to consider if that one is now an alpha. Okay, so we have this one in here is also equal to alpha. So this is now your alpha. So let us try to consider now that this is your tangent, or I'm going to consider that this one in here is an angle beta. So if you try to look at now the force F, so ito yung force F natin. So this is the force F. Then we have in the horizontal, so this is therefore your F in the x-axis. So that is F in the x-axis. And this one in here is the component of F in the y-axis. So we have your F of x, and this is now your F of y. So this is now your F. Now, so that your F of y is equal to 80 newtons, because the first F in here is 40I plus 80J. And your Fx in here is equal to 40. Hence, that is therefore your beta. So that your beta in here is now equal to the arc tangent of 80 all over 4t. And this is therefore equal to 63.4 degrees. So that is equal to 63.4 degrees. So that if you're now going to get your theta, so your theta is now equal to beta minus alpha. So your theta in here is equal to 63.4 degrees minus 22.6 degrees. And that is equal to 40.8 degrees. Let us try to determine now the tangential component. So we did consider this one. Okay, from your point O, so we have the tangential component of the first F is now equal to. So let us try to determine the magnitude of the first F. So the magnitude of the first F is now equal to the square root of Fx squared, so that is 40 squared plus Fy squared, or this is equal to 80 squared. So that one is now equal to 89.443 newtons. So the component of the force F and the tangential axis, so this is your tangential axis. Okay, so diretso siya sa point O. So we now have the tangential component. In the tangential component is now equal to F, which is equal to 89.443 newtons cosine of theta. That is cosine of theta, and theta is 40.8 degrees. So this is equal to 67.708 newtons. And the normal component is the magnitude of that force, that is now sine. Okay, your theta is included in the x-axis, in the tangential axis, so it is sine in the normal axis. So sine of 40.8 degrees. And this one is equal to 58.444 newtons. Now, let us try to apply now the your Varignon's theorem. So that the moment of the force F about point O is now equal to your Ft, the tangential component, multiply this one by, okay, I'm just going to place it in there 0, although because it passes through your moment center, and therefore we do not have moment arm. The moment arm is 0, or the lever arm is 0. And you try to take note in here now that if you are getting the moment of a force and that force passes through the moment center, its moment is equal to 0. And then we now have, so this is, we still assume counterclockwise is positive, so that is counterclockwise. So we have plus your f of n, multiply this one by the perpendicular distance from the moment center to the line of action of that force. So that is 90 degrees. So we now have your distance. I would say that one is now your A. So multiply this one by the distance OA. So how are we going to determine now? Your distance OA is now equal to the square root of 0.36 square plus 0.15 square. And this is therefore equal to 0.39 meters. So we now have the moment of the force F about point O. So the tangential component passes through the moment center, hence the moment about that point is 0. So plus Fn, and your Fn is 58.444 newtons. Multiply this one by the moment arm, 0.39 meters. So this is equal to 22.8 Newton meter. Again, that is positive. So that is a counterclockwise. Proceed to next example. Determine the moment of the 650 pound force at points O and point B. So this is your point B. We have your point B. So again, let us try to apply your Varignon's theorem. So let us try to determine now the component, the x and y component of the force equal to 650 pounds. So we have your fx is now equal to, so we have this one is equal to 28 degrees. So fx is equal to 650. We have cosine of 28 degrees. And that is equal to, so that is equal to 573.916. And your fy is equal to 650 sine of 28 degrees. And this one is